All right, so thanks for being there. Just before I start, I will not play the attribution game, so I won't tell. I should not tell any names during that presentation. I'll just show you some tricks that actually you can do that will kind of mimic real hardware implants that you can do at home if you like. So how did I start exactly? So we saw the big news there. Sorry, I said, okay, no names there. So I fixed that using GIMP. A lot of skills there, so that's fine. So actually, there was a huge article about people implanting hardware stuff into motherboards that could potentially access the CPU, the RAM, etc., and send that through the network, and that was a big thing, etc. And yeah, a lot of people were saying, yes, that's possible, no, that's not. Yes, it's doable, no, it's not. But there was no technical article about how to do it exactly. So this is the purpose of that presentation. So in one of the part of the article, there was that specific phrase: the legitimate server was communicating one way and the implant another, but all the traffic appeared to be coming from the same trusted server. So that's particular thing was like bothering me, because that would mean that in some way there is something that could access some of the parts of the motherboard without the host knowing it. So exactly how is that possible? So basically I need to check that. If you see the picture there, you see that that specific implant has like 3 pins. So that's not a lot of signals that you can actually use to make an implant. So only 3 pins to play with the Ethernet card. It sounds really too good to be true. So first thing to do, let's play with let's use Google. Try to find some information, etc. I found nothing. Maybe my Google foo is not that good, but I didn't find anything, so I better check it out by myself. Let's start. So first thing is, if you know about servers, etc., you know about IPMI. Everybody knows what IPMI is? Okay, so basically it's an out-of-band management for servers. Normally you have on different vendors, they have different names, iDRAC, ILO, etc. They normally use a separate network interface, but there are cases where you can use the same interface to access, to use the out-of-band management. How does it work exactly in practice? So within the IPMI, you have the central part there, which is called the BMC, Baseband Management Controller, which is the central core of the out-of-band management of your server. And this is the image from Wikipedia. And if you just look there, you have the NIC, Network Interface Card, and SM bus with a nice word, which is sideband. It looks really a lot like what the article said, like you use the same network card, but for sideband access for other stuff. So let's dig into that. What is exactly SM bus? SM bus is a system management bus. It's derived from another protocol, which is called I2C. And again, from Wikipedia, it's a single-ended, simple 2-wire bus. Looks really good because remember you were on the picture before, we had like 3 wires, 3 pins. And there, with only 2 wires, you should be able to communicate with a network card and maybe do some nasty stuff. We will see that later. So that looks really promising. So with knowing the fact that SM bus is available on some NICs, and that SM bus uses only 2 wires, I started to look for hardware that actually uses that specific SM bus. Using SM bus. So unfortunately, I didn't have any servers available at home. So I found on the internet, on some websites, the PCI Express cards, network cards, that are using that specific chipset. And if you look at the information on the website, you see that there is something that is called SMBus pass-through on that specific chipset. This is a good thing, so I ordered some of those boards and start to look at the datasheet. Datasheet is basically everything you need to know about that chipset. It's a nice PDF of about 500 pages. And yeah, I read a lot of that to understand exactly how it works. So that would be the motto of that talk. Everything you need to know is in the datasheet, because what I will show you there, everything is written in the datasheet, so there's nothing new, nothing special. It's just reading the datasheet and applying what is actually publicly available on the vendor's documentation. So first of all, we need to have access to SMBus on the card. So first part is locate the signals on that chip. So what do? We take the data sheet and we have that nice picture with the pins there that I need to access, because it's written in the data sheet. You have all the information about which pin does what, blah, blah, blah. So to make it easier for you, that's just those 3 pins. So, okay, that's fine. We have the chip there, which is this one here. And so somewhere there, we should have our 3 signals that go somewhere. Cool. But how do we actually know where they are going to? So we take some pictures using a camera, and we have our 3 pins, which are there, which are those 3 there. So it's those ones. So basically, you just use your GIMP skills to trace those signals. Unfortunately, we see that they are going through those kind of small holes, which are called vias. What are vias exactly? It's a way for people designing PCBs to actually send the signal to the other side of the PCB. The thing understands? Yeah, cool. So how do we do that to trace all of those signals? I used GIMP. You take pictures of one side of the board, then the other side. Then using GIMP, you you arrange the 2 images to align them to have the 2 vias mapped together. If I do this that way, you see that the vias are correctly aligned. So, once we know that those are the signals that we are looking for, again, we are just following them on one side of the board, then on the next side. That is good. So let's follow that to the end of the board, and we see that they are going directly to those 3 headers that were actually the only ones on the board. So I spent a lot of time for absolutely nothing because they were already there. So that was fun, but not really useful. Once you know that, it's kind of obvious, but okay. So what I did now was soldering some headers there, connecting a device that actually speaks I2C. And once I'm connecting, I should be able to actually send commands to the card and back. That is the easy plan. To do that, I use what I said, I2C. I2C, what is exactly? It's for integrated circuits. It uses 2 lines. The data line, which is used to send the 0s and the 1s on the wire. And the other one is the clock line. Basically, when you use a signal, you need to synchronize between 2 devices. And to synchronize that, you use the clock line, which goes from 0 to 1 to 0 to 1. And each time the clock goes from 0 to 1, you have to send a bit using the data line. So quite a simple protocol. A good thing in the protocol is that after each byte, so after 8 bits you send, you need to send another clock pulse, and that time it's the slave, so the device at the other end of the bus, that needs to send you an acknowledgement. This is the protocol, which is really good because we'll see that later. We can, in that way, know exactly when the card stops taking our input because we did something wrong or stuff like this. Still in I2C, all devices have an address because it's a bus. It's pretty much like on a network. Every device on a network has an address. It's the same for I2C. By default, the address is on 7 bits. So you have to, when you send a communication, you have, as the master, you have to send what is called a start bit. It's a way for the master to say, okay, I will start a new transaction on the bus. Then you send the address. If a slave is at that specific address, it needs to acknowledge that address. And once it's done, the master needs to send the commands, so it will send clock pulses and the zeros, the ones, etc. And after each 8 bits, the slave needs to send an acknowledge. So you can basically follow the communication using that specific way. So as I said, there the master sends the address, and there's an acknowledge sent back by the slave if something is responding to that specific address. Since I actually didn't know exactly what was the address of the card on the bus, I just used, basically it's like a port scan. You just ask for every address, and if you receive an acknowledge back, that means something is actually responding to that address. Unfortunately, on my test cards, the I2C didn't give any results, so that means the SMBus is actually not working. I was a bit disappointed. I didn't know exactly what to do. So what I did was read the documentation again, and in the documentation it says, okay, so all the settings are stored in an EEPROM. There, an EEPROM is basically just a small memory that is available to the card. And all of the settings are stored on that specific chip, which is there. So I used the tool to actually read everything from that EEPROM. And again, you just need to read the datasheet, follow that, and you will see that you need to change 2 different values, which are documented again by the vendor. So that's cool. So you need to change the address there to set the management interface to enable that. So you need to change that specific bit from 0 to 1. And on that part too, you need to change that specific bit from 0 to 1. So once I read all the data from the EEPROM, I changed the bits, flashed the EEPROM again, rebooted the machine here, and I didn't have any card. The card was not there. I didn't have any ETH something, etc. So, okay, what the fuck? Get the documentation back, and I forgot to calculate the checksum. So, back to the documentation, you read, so the checksum word is stored at that specific address on the EEPROM. And it says that you need that the checksum, the sum of all the bytes on the EEPROM needs to be equal to BABA. That's a value they specified directly. So using just a bit of Python, I just calculated the new checksum, changed it on the flash dump, flashed the dump on the EEPROM again, rebooted the machine, and now if I use the scanning on the I2C bus, I have access to something. Something responds to the address 0x49. That's great. For the next part of the talk, the address is still 49, but since the address is on 7 bits, you need to shift that by 1 bit, which is why you will see 0x92 in all the subsequent slides. So that's good. We already spent a lot of time reading the documentation. We now have access to the I2C bus. So what do we do now? We're starting to look at the datasheet again. So if you take the datasheet, you see a lot of different ways to communicate with the board. And the first command that you can see is basically ask the network card to give you back the MAC address. So you have that command there, that if you do the same way that's here, I show it live. You see that here I'm sending, that's basically the commands I use on my device to access the I2C bus. That command is basically an I2C start, to start a new transaction. You have the address of the NIC. Then the command that you need to send is D4, which is in the documentation. Then you need to tell the device, okay, now I will start to read data from you. Which device you want to read, it's always the same, the network card. Then I will read the first 2 bytes, because the first byte is the number of bytes that will be sent by the card back to us. The next one is basically the same ID, which means it's an answer to the request number 0xD4. And the next 6 bytes are those ones here, which are the same as those 6 bytes there. So for the moment, everything looks fine. I'm able to actually query the card and get some information back. That's good. But that's the basic stuff. We now need to be doing more stuff like this. So again, reading the documentation, you see that there is a command which is 0xC4, that when you use that command, then you need to send the size of a frame that you want to send on the network, and then the full frame that you want to send directly on the network. So that's good. If you are using that command, so our implant can ask the network card to send something on the network, which is good. Let's start with a small script. It is there. So basically what it does is I'm using Scapy here to generate a frame. So I'm just using a dummy source MAC address, dummy destination address. This is an IP packet, so I'm using the IPs for the demo. And it will be an ICMP packet, so it will be a ping, basically a ping. And just to show you that it works, I will add hello black Alps within the packet. So here I should be there. So this is my laptop here. Here I am on the implant machine. You can see that there. It's the implant machine. So if I send that command, it send me OK, send OK. And if I see there, I received the packet that I sent. That's good. What was really interesting in that case is that if I do a TCP dump on the implanted machine here, and if I repeat the same operation, okay. What happens? Ah, okay, there I see. There you see, it's only an echo reply. Okay, so basically my laptop there received the echo request, sent the echo reply, but the implanted machine did only see the echo reply and not the packet. So that means that that machine there just sent a packet on the network. But if you are a sysadmin and you are looking at the TCP dump, so you are looking at the traffic, you don't see the traffic that the network card sends. That means that you can actually hide traffic. You can actually send traffic from that host on the network without the host knowing it. So that's might be something good, and it really looks like the thing that was described in the first article. So if we are still reading the documentation, we see that there is a way to the network to actually get some traffic and send it to the BMC. Remember the BMC, the stuff for the out-of-band management? So again, everything is documented, and there is a way to for the network card to know if a specific packet that comes from the network, if it needs to go to the host, so basically the operating system of the machine, or if it needs to go to the BMC. And how does it work exactly? So you have the network there, the traffic comes here, and here there's a way to select traffic that will need to go to the BMC, so on our I2C bus, or if the traffic needs to go through the PCI Express to the host and the operating system, basically on the TCP dump part. And how does it work exactly? Actually, on that specific chipset, there are ways to select traffic from the source or destination TCP or UDP port, from the VLAN that is used on the packet, from the source IPv4 or IPv6, from the source MAC, etc. So that means that every packet that comes to that specific network interface can be filtered using those. And if one of the packet matches the filters, it will be sent to the SM bus and not on the PCI Express. So basically, you can make some traffic disappear from the network, and the operating system will not see that. Good thing is you have actually 7 different filters available, so you can create filters for a specific port or a specific source IP, etc. And all those filters are directly in the network card, and there's no way for the card for the host to know which traffic goes where, because the host actually doesn't see the traffic that is matched by the filters. So if you want to do exactly that in practice, how do we do that? First of all, we again look at the datasheet. And if you look at the datasheet a long time, you understand that you need to create a filter using a specific register there, and you need to use that specific command, which is 0xcc, with the specific parameters that are defined in another page of the document. And that specific page tells you, okay, so to add the filters, you need to set those specific bits at those specific addresses using that specific I2C command, blah, blah, blah. To simplify that, this is the command to actually set a filter on 2 predefined ports that are the common ports for IPMI. So if you send that command, if you take that it's the start bit, then the address, then the command to update the filters, then the number of bytes we will send to the card for it to process. Then number 61 is to update the filter register. And then there are 4 bytes for the filter register. The value is 00000C00, which means that only 2 bits are set. And those 2 bits, if you read the data sheet, you will see that that creates a filter for 2 specific ports, which are those 2. So if you set that up, you are able to actually create a filter. That's good. I tested it, but it's not the only thing you need to do, because you just created the filter, but you didn't tell the card that it needs to use those filters to actually process them. So you also need to read again the documentation to see that there is another command which is called legacy receive enable, which is that specific byte. So you need to create that specific command again. And you need to pass it a parameter with those specific bits that are set. Some of them needs to be at 1, otherwise the card will just return an error. And you need to add that bit specifically and that bit specifically to make the card actually process your filters that you created. So again, the command is there, that's good, but you need to know exactly how to read the packets from the NIC. And on that specific NICs, you have actually 4 different ways to read the frames. The first one is what is called the SMBus alert. That's basically there is a third signal that goes from 1 to 0 each time a packet is available for our implant to read. Another way is that the card actually starts to send by itself the packets on the I2C bus. That's another possibility, and there are 2 other ones. To make things simple, I only use the SMBus alert, so I'm still driving everything on the bus, driving the clock, driving the data, so I can just ask the network card, okay, so give me a packet if you have one, if you don't have, just send me dummy values. So, how do we exactly read frames? So now we have a filter that can process packets, so each time a packet comes from the network to the card, it will pass every filter that we set, and if it matches a filter, it will be sent to our implant and not to the host. But how do we exactly read those packets? Actually, if you read the documentation again, you have another command here, which is receive TCO packets. Yeah, because of course, there's in different chapters, it's not the same nomenclature, the same naming of the same functions. That's good. So you have the 0xC0 command, which when you send it to the NIC, it will reply with the size of the frame and some information about that frame and the bytes of the packet that was received by the card. So if we are doing a demo there, I will do exactly what I told you about. So the first one is, something strange here. Okay. So what I will do first is create a filter, a specific filter here. So I send the byte to start a new transaction, then the address of the card, then create a new filter. I will send 4 bytes for the parameters. The first one is, okay, I will create a new filter on a specific port. And the port I will be filtering is 0xA1, which is 161. Everybody knows what is the protocol with the port 161? SNMP, true. So then, once I created the filter, now I will use that filter on the device. So again, the command is cc for all the filtering commands. Then I will send 6 bytes, tell the device that I will use the filter I just created before. So I need to set that specific bit here in the register for the card to know that I want to process that specific port. And you can also see that every time I send a byte, I receive an acknowledgement from the network card. That means that all my commands are processed correctly. Now, what I need to do is enable the filtering stuff. there. And if everything works correctly, that would mean that if I ask the card to read some packets, I don't see anything for the moment. That's good. And if I do an SNMP, yeah, that's correct. Okay. Don't see anything, but I don't get anything else from there. Of course, demo effects, thank you. What doesn't work exactly? I'll try one more time. Okay, so of course, demo effect, thank you. Sorry about this. So basically, what should have appeared on the screen was that I'm sending SNMP requests to the implanted hosts. The host should show me, the implant should show me the packets that was received. And if I do a TCP dump on the host, I won't see any SNMP traffic coming in. Okay, so I'm able now to actually select which traffic I want the host to see and which traffic I just want to keep for my implants and nothing more. So this is cool. In that case, we can create a really good covered channel because basically we just make some traffic disappear. So now we can receive packets for, as an implant, we can receive some packets, process them, and send responses back to our CNC, for example. The other thing that is cool is that you can actually remove traffic. So if you are a sysadmin and you ask the networking team, I don't see any traffic coming in, the network team will say, okay, but on my switch, I see traffic going to your machine. And the sysadmin will say, no, but using TCP dump, I don't see any traffic. What happens? So you can really drive a sysadmin crazy using this. That could be a fun thing to do. But there's more to do that, because just making some traffic disappear is not really stealthy. So I think we can do better. And again, if you read the datasheet again, you see that there is another register, which is called manc2h. And that specific register is basically the register that tells, okay, so if there is traffic matching a specific filter that we created before, then if that filter is matching, then you can send the traffic both on the SM bus, the I2C, and on the PCI Express part. So basically, we're just sniffing traffic coming from the host. The host is still seeing the traffic, but our implant is doing the same thing for us. So again, the command to do this is this one here. And you need to set a specific register value that you can understand by reading the documentation. And you need to set the last bit because we set the first filter. Then this is the first bit that says that sets the first filter. And in that case, if the demo was working, again, I'm sorry for this. You should see that on the implant, we can receive the traffic, but from the network side, you can actually see the SNMP query and you get the response back. So this is great. There's a way to sniff traffic and still making the network work correctly, which is good. So using our implants, now we are able to create a covered channel, so traffic that, so we can receive and send traffic that will not be seen by the host. That does not mean that it will be seen by the network. So if you have an idea or something, it will still be seen because it's physically on the network, but from the implanted host's point of view, the traffic is never appeared. That's good. We are also able to sniff traffic coming from the network, which is good because, you normally have a lot of secrets traveling to the network, especially if you have a trusted network for your servers. And again, as a bonus, we can send any frame we want directly on the network. So in the previous demo, I used Scapy to create a correct packet. But basically, if you just send random bytes, the network card will just send random bytes on the network, which is good. So again, I'm sorry for the demos, but that's the end of the presentation. In my conclusions, I would say that can it be done? So we've seen that from the network side, from the network card point of view, yes, it is possible. If you read the article, the article in the first place, it will tell you that it can also access to the CPU, the RAM, blah, 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 etc. To my knowledge, there's no way for the SM bus to access the CPU or the RAM of a host. Maybe I'm wrong, but from what I've seen, it's not possible. There's, in some cases, a way for the SM bus to access the BIOS or the EFI on some motherboards. So maybe there's a way using the SM bus to actually do something nasty directly on the host side. Again, the best way for me, again, that's for me, the best way to be able to do everything that was written in the article is to be in that specific place. Because if you are at the BMC side, you have access to the network, as we've seen, well, actually we didn't, but bear with me. Access to the network, and you also have access to all the other buses, the LPC, so you have access to the South Bridge, and by that way you have access to all the peripherals of the server. So if I would have to design an implant, I would have placed it there. The thing is that, of course, the BMC is a rather big chip physically, so it's quite obvious if it's there. The thing is that on those, sometimes you can also change the firmware on the BMCs and maybe place some software that can be malicious. This is something that could be doable. Other thing is, could it be hidden directly on the motherboard? As we've seen for that specific thing, we only need 2 pins, so the clock and the data, plus of course, plus VCC and VDD, which is the power source for our implant, if we want to do this. The thing is that I2C is available on nearly all microcontrollers available. Even the small, an example is the small tiny 85. If I give you an example, this is a microcontroller, not tiny, and this is a memory chip that you can see on some motherboards. You've seen one of these EEPROM on the network card. So if I replace this one with this one, would you spot it just by looking at it? It would be quite difficult. If you read every chip, that's fine. If you're just looking for one of those, have you ever seen a motherboard? How many chips are there? Not easy, but again, that's the easiest way to do this. You just remove that one, place this one, and create a nice software to use an implant. Do you have one of the implants I presented there actually in your motherboard? I would say no, because on I2C the bitrate is 100 kilobytes per second, kilobits, sorry, per second. So if you have a gigabit NIC, you're not able to actually sniff everything, and yeah, it's more difficult. there is also, I just spoke about SMBus. There is another available sideband interface which is called NCSI, which uses a lot more signals. You don't have just two pins. You need to have around 10 something. So again, if you have more pins, you have more. The chip is bigger, and it's more difficult to hide. So there is a way to sniff traffic at the gigabit speed using that, but the implant will not be that stealthy. As a sysadmin or something, is someone trolling you with such implant? Unfortunately, from the host, you are not able to ask the network card if some of the registers I showed you are set or not. The only way to do it is actually to be connected directly on the SMBus and ask and query the card for the registers. So all those settings are set at runtime. So even if you are rebooting your machine, all the settings will be at 0. So there will be no filters, no duplicate traffic, etc., etc. So every time you reboot the machine, if you have an implant somewhere, the implant needs to send commands to the card to actually have access to it. One of the questions is, has it been done that way? So is the motherboards from the article using the same things I did? I don't know. Maybe not. But that's a way to do what the article was saying. So again, what would be a better option than fiddling with the I2C bus, placing a new chip, blah blah blah, etc. Good thing is that, as I said, the BMC is using a specific software inside, so you can just replace the software from the BMC with a Trojanized one. From what I've seen by looking at some articles on Google or on some websites, it seems like some motherboard manufacturers that are using BMCs for IPMI do not use encryption for the firmware, do not validate or checksum the firmware. So people were actually able to change the firmware, flash it on the BMC, and do some other stuff. Good thing is, if you are on the BMC with your Trojan, as I said, you have access to the whole system, not only the NIC. So if you would ask me, I would say that's the better way. So I don't know if you, when you are getting a new hardware, a new server, etc., if you are actually checking if all the firmwares on your motherboard are at the correct version, or if you are actually verifying stuff. Maybe yes, maybe no, but I would say most of the time no. And that's it. I'm sorry for the demo. So if you have any questions, feel free.
Thank you for the great presentation. Any question?
If you dump the EEPROM of the NIC and you find that the SM bus is to 1, does it mean you have been compromised?
Not technically. That just means that there is something on the motherboard that is communicating using SM bus with the card. Most of the time, it will be the BMC. As I said, the BMC needs that specific access to control the card. So that would just mean that you have a BMC and it is able to use the network card to use the out-of-band access. So that would just mean also that it's the interface is enabled. That doesn't mean it is used.
Any other question?
Thank you. Do you know of any application using the NIC filtering capability, and what would be your take on why is it there?
Actually, the first purpose of that was to actually use actually lower the cost of using an out-of-band management access. It was the primary mean was to use the same network cable for both the out-of-band access and the network access, which might be useful. I would say no, because most of the time the good practice is to use a separate switch or separate VLAN, blah, blah, blah. So it was just for lowering the cost for operational purposes. That was the main usage for that. But again, as we've seen, there are documented ways to mess with that and use it for maybe more malicious purposes.
Last question. Is there a way to access to the EEPROM from the PCI port?
Not on that specific card. Maybe on some others. There are some of the cards. If I check the picture back, I didn't show that to you, but there maybe I have a better image. Okay, there. Here you see that this is the EEPROM from there, and the only wiring is directly to the chip. So there's no way to actually use that. Good thing is that on some of the cards you can use ATH2 on Linux to actually ask the card for the EEPROM. Some of the cards, like Intel ones, actually allows you to dump the EEPROM from there, but that's not always the case. Another thing that I didn't mention is that, as we've seen, I spent a lot of time routing the traffic, the wires to the headers there. But there are also the same wires also go down to the PCI Express here. So the SM bus is actually going right there, and I took the PCI Express documentation, and there are actually two pins in the PCI Express documentation that are used for the SM bus. Nice. So on that card, the signal is cut somewhere there, but you should be able to actually wire it to the PCI Express and access it from somewhere else on the motherboard.
Nice. Thank you for the great talk, and also thank you for all the work as organizer of Black Alps.
Thanks. Thank you.